last lecture we have discussed cam follower systems, and we had discussed two types of followers, namely translating follower and oscillating follower. For smooth functioning of a cam follower mechanism, it is imperative that the follower should move smoothly without requiring too much of input power. That means the follower should not jam during its movement. Of course, the chance of jamming is more in case of a translating follower. While designing a cam follower system, care must be taken such that a translating follower does not jam in its prismatic guide. We have already seen that the chances of the restriction to the movement of the oscillating follower is much less, and we need not worry so much when the follower is oscillating. Now, a complete dynamic analysis of this translating follower is beyond the scope of this course, because this course is restricted only to the kinematics. However, a simplified static analysis can highlight the basic features, and that is what we are going to start right now. First, we discuss the case of a roller follower. Suppose the cam is rotating in the counterclockwise direction at constant speed, and the roller follower is mounted in an offset manner as shown in this figure. This distance, as we know, is called the amount of offset, the positive offset, because it is rotating in the counterclockwise direction. Now, we are doing a static analysis. That means we will not talk of the acceleration of the follower. Now, if we neglect the friction between the roller and the cam surface, then the driving force onto the follower is along this common normal, which we call Fn. And the direction of the velocity of this point of the roller center, that is the point of the follower or the trace point, is in the vertical direction. So, this is the direction of the velocity. And this angle between the direction of the velocity and direction of the normal force we defined as pressure angle phi. As we know, due to this force Fn, there is a tendency of the follower to cock or rotate clockwise within its guide. Let the guide length is Lg. This is the length of the guide, which, as we will see, will be an important parameter. And let us say this distance from the roller center to the lower end of the guide is L1. Now, we know there is a spring which connects this fixed link 1 and the follower. There is a spring here. So, as the follower is pushed away from the cam center, the spring is compressed. Now, if I take a larger view of the guide, this is the prismatic pair, and due to this force the follower gets tilted and this will be the situation. So, there is contact here at this end of the guide and this end of the guide. At these 2 points contact forces are generated. Of course, this gap has been shown much wider, this gap is very small, the angle of tilt is not so much. Now, what we do, we take the free body diagram of this roller follower, let us say this point is B and this point is A, and we neglect the tilting of the roller, I still draw it vertical. The forces that are acting is this driving force Fn, there will be a spring force downward as the spring is compressed. Let us say this is a spring force which I write Fs, and at this point A there will be a normal force, say N2, and at this end there is a normal force, say N1, and this distance we have taken to be length of the guide as Lg, and the distance of the point B from this point, this we have called L1, and this angle is the pressure angle phi. So, as we said, we are neglecting the acceleration of the follower, so we do a static analysis and see the relationship between these forces. If there is no acceleration of the follower, then the system must be in equilibrium. So, if I take the horizontal forces, we get N1 is equal to N2 plus Fn, that is this driving force, and sin phi. If we take the vertical forces, we get, at this point we are saying it has just started moving, so the frictional forces I can show will be downward because the follower is trying to go upward, mu N2, and at this point there is a force downward, mu N1. So, at the point B I have N1 and mu N1, and at point A I have N2 and mu N2. So, the vertical forces gives me Fn cosine phi is equal to Fs plus mu times N1 plus N2. And if we take the moments of all the forces about the roller center, then Fs, Fn, mu N2, mu N1, these forces are not producing any moment. The moment due to these forces are negligible because this angle is very small, it is almost vertical. So, the only moments are due to N1 and N2, and that gives me N1 into L1 must be equal to N2 into L1 plus Lg. So, if I substitute for, we can get N1 and N2 from here, solving these two equations, what we get is N1 is N2 into 1 plus Lg by L1. N1 is N2 into divided by L1, 1 plus Lg by L1. And substitute it here, we write N1 equal to this, so I write N2 into 1 plus Lg by L1 is equal to N2 plus Fn sin phi. I'll substitute for N1 here from this equation. So I get N2 is cancelled, so L1 by Lg into Fn sin phi. This is equal to N2 and N1 I can get from here. N1 is N2 Lg by L1, it gets cancelled, so Fn sin phi into 1 plus N1 is N2 into 1 L1 by Lg. This Lg by L1 gives me 1 and this 1 gives me L1 by Lg. Now, using the second equation, now I can write Fn cos phi equal to Fs plus mu times N1 plus N2, which is Fn sin phi into 1 plus 2 L1 by Lg. So you get the driving force Fn equal to Fs divided by cosine phi minus mu sin phi into 1 plus 2 L1 by Lg. So this is the driving force Fn, which ultimately this input member has to provide. Now what we see from this expression, that as phi increases, cos phi decreases and sin phi increases, so the denominator becomes small and Fn becomes too large. So as phi increases, Fn increases. Consequently, to have Fn within reasonable limit for smooth operation, I must not have phi too high. That is, phi should be less than some phi max, which we said is normally around 30 degrees. We also see that this Lg appears in this expression, so a proper guide length is necessary to control the value of Fn. The length of the guide is important. Of course, while follower is coming down, it is the spring force which pushes the roller down and keep in contact with the cam, and the pressure angle is not important. Phi is less important during the period during the what we call the return stroke. This is called the rising stroke and that is the return stroke during the return stroke. Stroke of the follower. And later on we shall see that this offset, the positive offset, will decrease the value of phi as compared to when the follower offset is 0. If the offset is 0, for the same movement of the follower and same cam, the pressure angle, maximum pressure angle will be more, and the maximum pressure angle will be reduced during the rise portion, during the movement that is going up. during this movement, when the follower is being pushed by the cam, and that is when the driving effort is necessary, the maximum value of phi will be reduced by having this positive offset, that is to the right when the rotation is counterclockwise. And during the return, as I said, the spring pushes the follower down and the value of the pressure angle is less important. We have just now had a simple static analysis of a roller follower which is translating in its guides. Next, let us continue with a similar analysis, simplified static analysis for a flat face translating follower. So, we have a flat face translating This is the diagram of a cam and a translating flat face follower. This is the prismatic pair between the follower and the fixed link. Now, here what we see, if we neglect the friction force between the follower and the cam surface, the driving force is along this common normal. Due to this force, the follower has a tendency to rotate in the counterclockwise direction and contact will take place here and there. So, this contact point let me say A and this contact point let me call B. As I said, the tilting has been shown exaggeratedly. Actually, it is little bit away from the vertical, so I still draw it vertical. So, this is the representation of this follower, and at the point A there is a normal force, say N1, and at the point B there is a normal force N2. Here there is a normal driving force which we call Fn. Because the follower is trying to go upward, the friction forces will be downward, will be mu N1, where mu is the coefficient of friction, and here it will be mu N2, and there is a spring that applies a force downward which we call Fs. So, if we consider that under these forces the follower is just going to lose its equilibrium, that means it is going to move upward, then horizontal force equilibrium gives me N1 equal to N2, and vertical force equilibrium gives me Fn equal to Fs plus mu times N1 plus N2. Now, this distance from the guide axis to the driving force we call eccentricity, and let me denote it by epsilon. This epsilon is called eccentricity of the driving effort. Eccentricity of the driving effort. In ideal condition, this eccentricity epsilon should have been 0. If I push it here, obviously it will go more smoothly. But due to this eccentricity E, because the contact point is here and the contact point will travel over this follower face, at this particular instant the contact point is here, and epsilon denotes the eccentricity of the driving effort, which is having this, producing this tilting tendency. So if I take moments about this point, and if I call this distance Lg, the length of the guide, as before. So what we find, that this moment is balanced by this moment of Fn, that is Fn into epsilon is N1 into Lg, because N1 is same as N2. These two forces are same, so they produce a pure couple of magnitude N1 into Lg. So this clearly tells me if eccentricity is more, then N1 will be more, and if N1 is more, N2 is equal to N1, so Fn will be large. So that tells me if epsilon is increases, Fn also increases. We can write the expression of Fn if we want. We can write Fn is Fs plus mu times 2n1, which is 2 Fn epsilon by Lg. So Fn is Fs by 1 minus 2 mu epsilon by Lg. If epsilon increases, then the denominator decreases, so Fn increases. So more is the eccentricity, that is this distance, more driving force is necessary. And this is more critical while going up, because you have to overcome the spring force. And this offset, as we shall see later, obviously decreases the eccentricity. Had this axis been here, the eccentricity would have been so much, and now the eccentricity has been reduced by this amount of offset. So this explains the importance of the free running of the follower in the cam follower system. Now that we have discussed the importance of the pressure angle and the eccentricity in case of roller follower and flat face follower respectively, our next task is to how to design the cam profile, that is how to synthesize the cam profile if the desired motion of the follower has to be generated. But before getting into that, let us see how do we describe the follower motion, that is description of the follower motion. How do I describe the desired follower motion? As in the case of linkage synthesis, we can use either graphical method or analytical method for cam profile synthesis. And accordingly, this follower motion can be described in terms of a diagram if we want to apply a graphical method, or in terms of an analytic expression if we want to have an analytical method. So we say graphical description and analytical expression. in the graphical description, which we call a displacement diagram. We plot the displacement of the trace point, which we denote by y. Y is the displacement of the trace point, that is the roller center, or the in case of flat face, it is the axis of the follower where it is intersecting the flat face, a particular point of the follower face, that is called the trace point. So we plot the displacement of the trace point versus rotation of the cam, say represented by theta. Obviously, this y versus theta is a periodic function. As cam rotates from 0 to 2 pi, everything gets repeated. This is one cycle of the cam rotation. Now, normally when the cam, this y is measured from the lowest point, that is when it is nearest to the cam center. If we go back to the diagram, if this is the cam and the corresponding base circle, and let us say this is a pitch curve and the corresponding prime circle, which we have defined in our last lecture. As we know, if this is the roller center, which is the trace point, this lowest point of the roller center is here. It can never get into the prime circle because the roller surface cannot get inside the base circle. When the roller is touching the cam along this base circle, this is the lowest point of the roller center when it intersects the prime circle. So this is the lowest level that the trace point can come, and we measure y from here. So this follower displacement is measured with y equal to 0 at this point. Now, normally the follower, as it goes up, y is positive, y always remains positive, it goes up away from this cam center. After that, there may be follower does not move, there is a dual period. This is called dual period. After this some dual period, follower return to the same level and again has a dual period. These are the typical diagram for the automobile valve. The valve opens, is kept open, returns, gets closed and remains closed, and then again open. So this is again a dual period. When the cam goes away from the lowest position, this is called, this duration is called the rise, and this is called return. For normally at least in automobile cams, for operating the valves, we have a rise when the valve is open, then the valve is kept open, there is a dual, the follower does not move, then valve gets closed, the follower comes down, and then the valve is kept closed and the follower does not move, it follows a dual. So we have a rise, dual, return, dual. And it is this maximum displacement of the follower, this is called lift. We will denote lift by the symbol L. The value of theta during which the rise takes place, we call it theta rise. Then this dual period we call theta dual 1 because it is the first dual period, and this angular interval we call theta return, which is followed by again another dual theta d2. We should remember that normally the disk cam rotates at constant speeds, so theta is omega 2t, where omega 2 is constant, so this theta is nothing but representing time. So this is the graphical description of the follower motion, and this diagram is called displacement diagram. Let me now repeat what we have explained just now, that we are talking of a roller follower which is translating. This is the cam profile, this is the pitch curve, this is the base circle, and this is the prime circle. As we know that the lowest point that the roller center can come is here. It can never get into the prime circle because then the roller will get into the base circle. The movement of the follower is measured from this lowest level. So this distance y is called the displacement of the follower. Y is always positive. It starts from here, goes up and comes down. Y always remains positive. The velocity is positive, that is dy dt is positive during the rise period. Dy dt and all derivatives of y remains constant, so all derivatives of y remains 0 during the dual period. Then velocity is negative while it is the return period, and again y remains 0 during the second dual period. Just now we have seen how we describe the displacement of a translating follower. Now let us look at this picture which shows a roller follower but which is oscillating. The roller follower is hinged at O3 and this is oscillating. Again, this is the cam surface or cam profile. This is the base circle. This curve is the pitch curve, and this circle is the prime circle. As the roller follower oscillates, the lowest point that the stress point can come, the stress point moves in a circle with O3 as center, is moving along this circle. So this is the lowest point of the stress point, the roller center, and this is the this is the follower O3A. This is the lowest position of A. Let me call it A1. Now here there are two more dimensions, that is how this O3 is placed with respect to the cam center O2. Here we have shown only A, but there can be a vertical distance also which could have been B, which has been taken 0 in this diagram. So this is the lowest position of the follower, and it oscillates from here and comes down up to this point. It can never go below this level. So this is how we measure the displacement of the oscillating follower by this angle psi measured from this O3A1. This angle is psi, and this psi B will be decided by the other dimensions, the angle from this lowest position from the line O2, O3. And the movement of this will be L times psi along this circular arc, where L is the length O3A. So this is how we describe the movement of the follower, the psi as a function of cam rotation theta, whereas previously for the translating follower we had y, the movement of the follower, as a function of cam rotation theta. Next we shall discuss some typical basic motion of the follower which are used. The next topic of our discussion is the basic follower motions. Those are the motions of the follower which are normally desired, and we group it as basic follower motion. The first one we discuss is known as uniform motion. By uniform motion we mean that both the rise and return of the follower takes place with constant velocity. So if we look at the displacement diagram, say this is theta Ri, this is theta D1, this is theta return, and this is theta D2, and this whole thing is 2 pi. The lift of the follower is, say, L. So the displacement diagram is very simple in this case, that during this rotation from 0 to theta Ri, it attains a distance L and moves with constant velocity. Because theta is proportional to t, so this you can think of as well a time scale. The theta scale is same as a time scale, so uniform velocity means it is a linear motion. Then here it remains at L. During this rotation of the follower, during theta return, it comes back with constant velocity and then again remain at y equal to 0. So during this y is L, during this y is 0, during the two dual periods. During the return period, we can write as simply y equal to L into theta by theta Ri. This is valid for 0 less than theta less than theta Ri. This is the analytical expression for the same follower movement. As you have seen, during this rise period, the follower displacement y as a function of theta can be easily expressed by this linear function, y equal to L into theta by theta Ri. When theta is 0, y is 0, and when theta is theta Ri, y is L. This is what we call uniform motion. Mathematically, this motion is very simple, but we can see what are the undesirable features of such uniform motion. If we look at this point, that is this point, velocity was 0, and suddenly the velocity is constant, a constant velocity is being picked up, so acceleration here is infinity. So at theta equal to 0 and at theta equal to theta Ri, velocity changes suddenly. Here it changes from 0 to a positive velocity, and here it changes from positive velocity to 0 suddenly, which causes acceleration of the follower tending to infinity. That means a very large force is necessary to produce such acceleration of the follower. That is why we would like to modify this such that it takes off smoothly and also ends smoothly at the beginning of the rise and at the end of the rise. So what we can do, let us concentrate only during the rise period. Exactly similar treatment can be done for the return period. So now onwards we will consider only this rise period, theta going from 0 to theta Ri. If we want to have uniform motion, then bulk of the motion will take place at constant velocity, but at the beginning and at the end we draw a circular arc with this some point as center and this as circular arc, such that the tangent here is horizontal and tangent here is again horizontal. And these 2 points we can join with a straight line. So the bulk of the motion during the rise during this portion of the rise, that is most of the during the rise period, the velocity is uniform, but it is modified near the beginning and at the end. This is called modified uniform motion. This is the lift. So this is what we mean by description of the follower motion, and this is the basic follower motions. Only one we have discussed today, that is the simplest, which is uniform motion. But we have already seen what are the undesirable feature of this uniform motion, and it is this: to avoid infinite acceleration or infinite jerk, that is sudden change in acceleration, we have to think of more complicated motion than such simple uniform motion. But that is what we will discuss in our next lecture.